Hello, everybody. It's nearly time. It's nearly an hour. The timing is running very well, so congratulations to the previous lot. I'm Jeremy Gibbons. I'm chairing this session, this talk, really, and I think without further ado, I'll hand over to Mohammad Mousavi, who's going to talk about MDE for cyber physical systems. Off you go, Mohammad.
Thank you very much, Jeremy. And thanks to the organizers for inviting me. It's an honor to be here and to speak to this nice audience. My talk is organized in two parts. In the first part, I'll give a very broad overview of the different projects we have been involved in regarding model-driven engineering for cyber physical systems under a kind of a unifying motto, which I will present next. And the second part, I will focus on one of those projects, which is about environmental impact of vehicles. And how we have generalized that into some sort of model-based technique for analyzing cyber physical systems. So there will be a general part going through five different projects I recall, and then a more specific part. All of these projects have a common motto, common vision. The motto is trust in autonomous systems, and we kind of define this mission of our different projects, of our group, as applying rigorous analysis techniques, so model-based mathematical analysis techniques, to ensure safety and trust in autonomous systems. That's the unifying mission across all of these projects that I will present in a second. And by the way, I do appreciate receiving questions during the talk. So if you have any burning questions, anything that is unclear, or you would like to have more explanation, do stop me there, type in your question, and I would appreciate if Jeremy could warn me that there is a question to answer there. Thank you. So what do we mean by trust? Trust is an epistemic phenomenon, namely it's in the mind of the different stakeholders and users. If they believe that the system is helpful, so it's delivering a function that they expect to deliver, and it's safe, it's not going to harm them, particularly in very challenging scenarios, then they have trust in that system. And trust is not necessarily a positive thing. If you over-trust a system that is not trustworthy, and we'll see an example of such systems during the technical part of this talk, then that can harm you, that can harm the environment, that can harm the society. And under trust is also not a good thing, because then you are not using the functionality that the system is performing, because you are not trusting that the system is going to be safe to you. So having the right level of trust is basically our goal, and that's a very difficult goal to achieve, because that is a bit of a subjective judgment, whether you have the right level of trust or not. And we want to kind of quantify that in terms of a number of different contributors to trust. What are those contributors? The first one is technical transparency. If we could document, model, and also communicate those models of design decisions to the users, then we can achieve the right level of trust. And not in all sectors it's common to provide such documentation to users. So one of our main tasks across several of these projects is to learn models from those systems and show them to the users and ask them whether this is what they expected the system to be. And if it's not, then that can adjust the level of trust downwards, possibly, because the design intentions were not made clear to them in advance. Same goes for the runtime behavior of the system. If the system can produce explanation during the runtime, that could also adjust the level of trust to the system to the right level. If there is understandable evidence of safety and security, again, that can contribute to trust. And if the system communicates all of these in an understandable fashion to the different stakeholders, possibly using different types of explanation, different types of models to different stakeholders, then that type of user experience is going to influence trust as well. Let me give you a couple of examples of different projects we have been doing in this domain. One is about connected and autonomous vehicles. So what we did was to build models of connected platoons and do search-based conformance testing techniques. I will introduce conformance testing in sufficient details in the technical part of the talk. to find those scenarios that are likely to challenge the safety of the passengers of those vehicles. So the goal is, first of all, a platoon is a convoy of cars in which the leading car is driven by a human being, but the other cars follow the maneuvers of the leading car with a very minimal distance. And one of the goals is to reduce the air drag on the following cars, and also potentially reduce the cost of the human driver in the convoy. And what we did, we made a model of those connected vehicles. We made a model of the intervehicular communication across these vehicles, and then we automatically generated scenarios that are likely to push the convoy to its safety boundaries, leading to near crash scenarios or crash scenarios. And then we reported cases where the standard parameters of the protocol can still lead to unsafe behavior. And that's reported in this publication from 2 years ago at a communications conference. Then the piece of research that I will be focusing on today is about particle emission and environmental impact of vehicles. So what we did, we looked at diesel cars, and we tried to learn models of their emission behavior and present them to their users to show that they actually violate the environmental standards while they have passed them during the testing phase. So what we try to do is to maximize the emission of the car on their scenarios that are very much like their standard testing scenarios, and show that the car do violate them, possibly because they have some cheating device installed in them, and try to learn the pattern of a testing cycle, and avoid showing that type of bad behavior only during the test cycle, while when they are on the road, they will produce a lot of emission and a lot of pollution to the air. This is to kind of catch the cheaters, as we call it, but also this can be built into the design process of those vehicles by detecting those scenarios that are likely to lead to more pollution, and improving the design by following a different profile of for example, powertrain behavior to minimize the pollution. So it can be done both to catch incorrect behavior and behavior that is potentially damaging users' interest, but also it can be used in the design process to improve the design and build vehicles that are more environmental friendly. This is done for diesel cars, but the same principles can be applied to other types of cars, including electric cars, and then look at battery usage behavior, for example. And this is basically to build more transparency into the design of these cars. These cars passed, the cars that we have tested passed emission tests, and they are on the road, while our analysis shows that they have done something to pass the emission test, and then the actual emission is much higher in practice. So that's the second project. The third one is in general about model learning. So how can we learn succinct models from evolving systems? So it's a more abstract type of project we are performing. And the main issue we are studying in this project is to apply model learning to systems that change over time. Change could be due to, for example, an AI being retrained in the system, but it could also be due to new features being implemented, some features being fixed. How can we focus on those changes and learn new models for those evolving systems? The basic technique we use is called automata learning. It's based on Dana Englin's celebrated L-star algorithm, and we have built a few different extensions on top of that to address evolving systems and focus on system evolution. And we have a couple of publications, one from last year, one from 3 years ago in this area. Final project, one to the final project, and then I will focus on one of them and then give more technical details, is a project that is about a doll that was developed at the University of Hertfordshire for autistic children. It's called Caspar. This is the doll. And we are performing a project together with the University of Hertfordshire. The project is led by them. The doll is, by the way, commercialized by this Canadian company. And what we are doing is to generate explanation for the behavior of the doll in the interaction scenarios with children. So what we have done so far in the project is to analyze the interaction videos, coding them in terms of some events. We are now at the process of formalizing those interactions into some behavioral models, and then the goal is to generalize them into some models from which we can generate causal explanations for the different behaviors of the doll. At the same time, we are doing user studies to understand what type of explanations are found useful by children, by teachers, by parents, and kind of customize our explanation generation to what is actually useful for that type of user. And this is about trust through explanation. Finally, we have a very large project across 7 universities now. So King's is leading the project, but there are 6 other universities involved, which is under the umbrella of trustworthy autonomous systems. And we look at the issue of verifiability from a very broad perspective. So we have psychologists, we have people who do theorem proving, people who do model checking, testing people, people who do physical design and physical modeling of robots. So there's a whole scala of different expertise coming together. The goal is to build a unifying model-based framework that can translate these different aspects into a unifying semantic domain, and then study the interaction of all these different aspects that are relevant to the autonomous system design, and make a system-level verdict about system behavior and how it conforms to the different types of specifications we provide. So that was the more general part of the talk. My own expertise in all of this is something called model-based conformance testing, and that is something that I've been applying in all of these projects. Let me first explain the idea of model-based conformance testing in case you haven't seen this before, and then I will apply it to one of those specific projects and see how we can use it to do particle emission tests in this case. The idea is that we start with a test model, and often test models are not present or very much outdated. So updating that test model is an important issue by itself. For example, we can use automata learning techniques to update our test models, but that's beside the point. We started a test model, and then from that test model, there is an engine that can generate test cases and run it on the system on the test. Running test cases, abstract test cases on the system on the test is a non-trivial task because that requires concretization of the abstract test cases. But anyway, we have an interface that translates what the tool produces to the system on the test. Then we have an analyzer that observes the behavior of the system on the test with respect to those test cases, and then it can come up with a judgment whether the system has failed the test case and whether it's enough to stop the testing campaign, or we should continue this loop until we have either enough confidence that the system is performing well or enough failing test cases to have an evidence of what went wrong in the system on the test. So this is the practical part of conformance testing. And the theoretical part is to map all of these objects into a mathematical domain by providing a formal semantics, a mathematical semantics to the test model. So we will have a mathematical object representing our test model and some sort of hypothetical mathematical object that represents the class of possible implementations of that test model as a semantic model for the system on the test. Of course, this mathematical object is too large to generate, so we only assume its presence somewhere in Plato's caves, right? But our main task here is to define what it means for a system to be correct with respect to a conformance relation, right? So this conformance relation is a mathematical relation between two mathematical objects that defines what type of implementations are deemed correct with respect to the specification that we are considering. And the goal of the practical part is to only fail those test cases, those systems that fall outside that conformance relation. If that happens, if we can only fail those systems that fall outside the conformance relation, then our practical setting is sound. If we can fail all incorrect implementations, then our practical setting is exhaustive. And exhaustiveness is typically a very, very challenging thing in practice. there are lots of very good theories about exhaustive conformance testing. Many of my colleagues are working on that. But in practice, it's very difficult to realize them, and you need a very good fault model to confine the domain of conformance relation. Otherwise, they won't work. So this is what I typically use in all of these different projects. Of course, it's complemented by lots of other expertise from other colleagues, but that's the general idea. Let me focus on one example, which is about doping detection, so detecting malicious behavior in cyber-physical systems. And this is joint work with many people that are listed on the slides, and the credit goes to them. The remaining issues on the slides are all mine. Before I continue, are there any questions in the chat box, Jeremy, that I could answer?
There are questions, but for the end, so let's save them for the end.
Okay, that's fine. That's fine. Fine. So what do I mean by doping? So doping is a general phenomenon that we have seen it, of course, in the sport world, right? We have seen people who kind of inject some sort of substance into their blood or have some sort of food that changes their performance during competitions. And a similar phenomenon happens in systems engineering, namely people, it could be the manufacturers themselves, it could be malicious agents, they bring in components that change the system behavior against users' interests. An example that we'll see extensively during this talk is the diesel emission scandal. So many car manufacturers, vehicle manufacturers, they optimize the system behavior for certain scenarios. Those scenarios could be the emission tests that are performed in different countries, or they could also pertain to the different signals they show on the dashboard of the car, just to satisfy their users, while underneath, actually, the car can perform lots of other scenarios, can show different behavior in lots of other scenarios that are hidden from the user, and they're not shown to the user properly. So diesel emission scandal is just one example of a very common practice in engineering transport systems, where the information that is exposed to the user is only one optimal scenario, and many other scenarios that are actually happening in the system are not properly shown to the user, and they are hidden. So that is one type of doping, and I will, of course, talk much more about diesel emission scandal in the remainder of the talk. Another example is when you buy a laptop or a mobile phone, and against your will, the manufacturer disallows you to use the different types of accessories, including even cables for charging. Sometimes they detect it, and they do not allow you to use other cables to charge your laptop or your mobile phone. Third example is when a malware, for example, in a gaming app, starts detecting when you're not using your mobile phone, when the screen is off, when it's nighttime, for example, and it starts doing cryptocurrency mining on your mobile phone using your battery, your computing power on your mobile phone against your will. So those are examples of malicious behavior that we call doping. And the way we detect doping is assuming that the system is built to be robust. So we assume that this is not very early stages of system development. We look for behavior of the system in which small changes in input leads to very large changes in output that cannot be explained by the domain expert. So there is a domain expert in the loop to kind of look at those scenarios where we have identified that a small change in input will result in a large change in output that cannot be explained otherwise by any other means than having some sort of doping behavior in the system. For example, if we deviate from the test cycle of the car, of the vehicle, and we suddenly see a huge amount of additional particle emission in the exhaust of the car, from the exhaust of the car, then we know that something serious is happening there, and that can be used as part of our evidence for doping in that case. And of course, we accumulate these evidences until we have a legal case, if you want to go to the court, of course, and reason about this. I will get back to this issue of accumulating evidence at the end of the talk, because that's some ongoing work we are currently looking at. The second example is when you change, for example, the time of your mobile phone or the screen behavior of your mobile phone, and suddenly you see a sharp change in your battery usage or in CPU usage of your mobile phone. That's indicative of some sort of behavior that is very much dependent on the time, and you could investigate that further to find out which app is causing that, and finding a malware in the apps that are causing that type of malicious behavior. So those are two examples. I will again substantiate that example using cars. Is there a question?
Yeah, there is a question, clarifying question from Stefan Chala. Why do you classify such chaotic behavior as evidence of doping?
This is not necessarily chaotic. So if you look at those behavior where the system is behaving, for example, according to the standard, right? So we have a standard for particle emission tests. There's a European standard for particle emission tests. And the car is supposed to produce a certain amount of emission in those scenarios. Likewise, there is a profile of battery usage on a mobile phone. So this is not at all chaotic. That is a given scenario where you start. And then once you start deviating from that, mutating that behavior, right? So you start from a certain scenario, and then you start changing that behavior in small steps. And when you detect that a small step will cause a huge change in the output, you are going to investigate what is the cause for that discrepancy between input and output change, right? I will, of course, quantify that in more details, but you do have a starting point where the behavior is not chaotic. It's actually what you expect it to be, and you start changing that and searching around those pockets of reasonable behavior to see whether you can find something unreasonable in the behavior.
So I think it's the discontinuity in behavior.
Yeah, so the system is built to be robust. You don't expect that small changes will cause huge changes in the output. You're changing for counterexamples to robustness, kind of, right?
Well, or it's a stateful system, and what you've just probed is a change of state.
Absolutely. That's why you involve an expert there. So is that close to boundaries of a phase change or not? That's something that an expert can help you. And actually, we are building a model learning process in the loop so that we can help experts see when there is a phase change and there is not. Yes.
Right. Okay, good. Thank you.
Okay, so how do we quantify these changes? We quantify them using a notion of conformance, as I introduced at the beginning of the talk. And our notion of conformance is bound to look at dynamic behavior, so continuous behavior. And assume that, for example, you have a velocity of a car given by this black diagram here. So there is a basic velocity profile of the car, and you deviate from that by a little bit. So you measure the difference in terms of the amount of additional velocity that you experience in this, the maximum additional velocity that you experience in this other dotted red diagram. That quantifies how much change you have seen in the velocity, in the input domain of your car. If suddenly in the output domain you see a huge change in terms of the value of emission in terms of milligram per kilometer driven or whatever, then you will present that to the domain expert and ask whether this is something reasonable. Is it expected that if you increase the velocity by, say, 1/10 of a kilometer per hour, I can see like twice as much emission in terms of NOx emission in this car or not? This is one way to quantify the differences by looking at the point-wise changes in value of the continuous signals that you're observing, and then putting a bound on the input and output deviations, and checking whether there is a scenario in which a small change will cause something out of bound for the output. That's one level of change that you want to measure. The other one is phase change. So suppose the input signal is a bit delayed, like this black signal was my original signal, but because it was human-driven, this scenario, the human driver started the second signal slightly later, right? Then you want to measure also the maximum amount of time difference between the two signals, again, point-wise. And that can give you a measure of difference in time. You combine these two, that can give you some measure of difference in terms of time and value. And then you compare them. You have a predefined kind of error bound for your output. If that goes beyond the error bound, then you are reporting something suspicious as possible evidence for doping in these cases, right? And again, all of these are informed by the domain expert knowledge. Now, these are the basic ingredients of a conformance relation. How do we build a mathematical theory of conformance using these measures? The first one, so going back to my figure, I'm actually at the bottom part of this figure. Before going to the practical part, I am fixing the conformance relation, right? And there are a few different alternatives in the literature that we have studied and we have generalized for the purpose of our particle emission tests. The first one is due to this gentleman, Hussam Abbas. He did his PhD at Arizona State University 2-3 years ago. It's a very simple notion of conformance, whereby you define a measure of difference in time and in value, epsilon and tau, as I introduced in the previous slides. And then you say a signal is in the tau epsilon vicinity of another signal. So in this case, the blue signal is in the tau epsilon vicinity of the black signal. If for each and every point on the blue signal, there is a point on the black signal that is not more than tau apart in time, so not more than tau apart in time, and not more than epsilon apart in value. So for every point like this red point over here, there is a point on the black signal that falls in the box that is 2 tau wide and 2 epsilon, 2 tau long and 2 epsilon wide, right? If that is the case for each and every point on both signals, then these two signals, tau epsilon, conform to each other. There is a second notion, which is called scorocode distance. That's also used in stochastic systems, but I'm going to skip through that given the time. The difference between a scorocode distance and tau epsilon conformance is that the change in tau and epsilon is not necessarily monotonic in this notion of conformance. So you can have points that are related to the future point, and then suddenly a next point can be related to the past point. So the changes in tau and epsilon are not necessarily monotonic. A scorocode distance forces you to have a monotonic change in tau and epsilon throughout your conformance checking. I'm not going to talk about that. This is due to Gio Deshmukh at University of South California. Now, what we did, we took all these different notions that are in the literature and we built a generalized theory of conformance for continuous systems that defines when two signals are conforming to each other with respect to something called the retiming function. So given a class of retiming function, you can recover each of those past notions of conformance. So we have shown that the past notions can be recovered using this generalized theory of conformance, but also we can come up with new notions that haven't been introduced in the literature and are useful in practical context. What is a retiming function? A retiming function is a mapping from the time domain of the two signals you're from the time domain of the signal you're comparing to the time signal of the signal that is being compared with, and it is supposed to be a one-to-one mapping of points in the time domain. We say that two trajectories are tau epsilon conforming given a retiming function, where if for every point that you pick in one signal, the retiming of that point in the other signal is at most tau apart and at most epsilon apart from the point you have picked. And by fixing the different classes of retiming function, as I said, you can recover the old notions. A system is called doping clean when for every two valid inputs that are tau epsilon conforming to each other, the outputs generated from those inputs are also tau primed epsilon primed conforming, and the tau and epsilon and tau primed and epsilon primed are defined by the domain. So in the domain of particle emission test, this is given by the standards of particle emission test. If you are using it for a different domain, you should find out what the right margins for tau and epsilon are reasonable for that domain and use this theory for checking doping cleanliness. So that's our basic theory. What we are going to do next is to develop a machinery that can apply this theory in practice and use that to test actual cars.
Mohammad, you just have a couple of minutes left. So,
Okay, okay, fine. Then I will. So we have formalized this theory in terms of a logic. This logic is called, let me go a bit further. This logic is called hyper STL. STL is an extension of temporal logic where you can specify time bounds on the differences of signals. So in addition to usual temporal operators, you have intervals where you specify time bounds. And it's a hyper logic because you can pick a set of traces and compare them to each other. So that was the logical formalization of this. We wrote a monitoring algorithm to, on top of this logic to check for conformance. We specified conformance in this logic. We defined a monitoring algorithm to check for conformance on top of this logic. And then we applied it to an actual car. So this is the car that we used. We brought it to our colleagues at a Powertrain Research Center. So they were doing actual tests on cars. And we took a European standard for particle emission, right? We started modifying the driving behavior that is specified by the standard. And the driving behavior specified by the standard starts with 4 urban scenarios. So each of these 3 cycles is an urban scenario. You do 4 urban scenarios, and then you do a motorway scenario. And then you have to leave the car for a day to cool down, and then you can do another test. What we did, we started tweaking these scenarios by, for example, superimposing some sine waves on top of them, very small ones that are not visible and are still admissible by the standard. And later on, we started modifying the signals by mutating the urban scenarios so that, for example, the smaller peak happens after the medium peak rather than the other way around. And we found very interesting outcomes that I will present as my final slide for this talk. So if you look at the blue scenarios, those are the actual scenarios that are specified by the new European standard for particle emission. And then the black one is the one that we drove by mutating the blue one, in which, for example, in the first cycle, instead of starting with the first urban sub-scenario, we started with the second one. So you start with the second one, then you go to the third one, and then you drive the first one, and vice versa, you are doing something different here. You start with the third one, then you do the first one, and then you do the second one, etc. And then you do the motorway as expected without much deviation. So that's just the result of the human error in driving those scenarios. Now, what we observed is very interesting. The orange line is the amount of emission when you drive the black scenario. So that's the usual scenario for the European cycle. While if you drive the blue one, in which you mutated the order of those urban scenarios, note that the the velocity profile is exactly the same. We are not driving any further. We are not driving in any different velocity. We are just mutating some orders of those behaviors. We see a completely different profile of emission. If we drive the usual European cycle, we get 182 milligrams per kilometer driven, which is way above the standard, by the way. The standard says you have to have a maximum particle emission of 80 milligrams per kilometer driven. So this car shouldn't be on the road anyway. But if you tweak the scenario and kind of mislead the cheating device, if there is any cheating device in that car, you suddenly get 5 times more emission than what is allowed. So you get about 400 milligrams per kilometer driven. And you see at a certain point, apparently the car loses track of what you're doing. So it starts deviating from the optimized scenario. And then suddenly you see a huge amount of additional NOx, suggesting that there might be something going on in that car. And we have applied that to other makes of the car. So we have applied it not only to this particular brand, but to other brands. And this has led to lots of very interesting interactions with the car manufacturers in the meantime. So let me conclude what we have done. We have defined an informal notion of doping. We have formalized it using a general theory of conformance, using these retiming functions. We have a logical characterization of that notion of conformance using hyperlogic based on STL, signal temporal logic. We have a monitoring algorithm for STL, and we applied it to actual cars. This is only one of the examples. If you go to the paper, which is published this year at Logical Methods in Computer Science, you can see several other examples where we have shown possibly cheating behavior in this particular car. Our colleagues in Germany have applied it to, I think, 2 or 3 other makes of cars and have found similar, slightly different because there are different explanations what the car is doing, but similar type of behavior in those brands of car. So I think I will conclude by this slide in which we summarize the future research in this area. What we have been doing is mostly generating scenarios by hand, for example, by mutating the standard behavior. But what we would like to do in the future is to learn some sort of hybrid stochastic model from the scenarios we have driven so far, and then use a conformance testing engine to select from the purported model of the behavior of the car those scenarios that are likely to reveal doping, and loop as long as needed until we have enough evidence for doping, and then feed that into a causal analysis tool in which we can pinpoint what is a possible cause for this doping behavior, and report that to pursue that further, for example, if we want to make a legal case out of that. And with that, I would like to conclude and receive your questions. Thank you very much.